Now we are taking related rate questions. A particle is moving along the curve given by the equation y equals 4 square root of 3x plus 13. As the particle passes through the point 4, 20, its x coordinate is increasing at a rate of 4 units per second. We need to find the rate at which the y coordinate changes. So what is given? The function y equals 4 square root of 3x plus 13. And we are also given x equals 4. We sometimes call it x1. And y1 is y coordinate 20. And the rate of change of x coordinate is 4. So we write dx dt. This time is involved in this derivative. So what is our goal? To find dy dt, rate of change of y. For simplicity, we take the square on both sides. So we get y squared equals 16 and then 3x plus 13. Otherwise, we have to use derivative with this complicated term. But if you do like this and use the implicit derivative, it will be very easy to find dy dt. So now we are taking derivative with respect to t. So y square will be 2y and then dy dt. Now we have 48x, so we get 48 dx dt. There is a free constant, goes to 0. We are given x equals 4, y equals 20 already in the problem. So we can plug all these values in here. Y is 20. Plug it and solve for dy dt. So you got dy dt is 24 over 5. This is the rate of change of y coordinate. Next question. It's a very similar one, but we have different information in this. A particle is moving along the curve given by the equation y equals 4 square root of 3x plus 13. As the particle passes through the point 4, 20, its x coordinate is increasing at a rate of 4 units per second. We say find the rate of change of distance of the particle to the origin at this instant. So let us look at what information we have. Given y equals the function, x equals 4 and dx dt is 4. So if x is 4, then y is given 20, so we write there. And let us take the point xy on the graph because we need to find the distance from origin. You can compare this problem with the previous one. So the xy point will be on the graph and we are interested to see how this distance is changing. Is the point is here, this is the distance. So distance is changing every time when the particle is moving or the point is moving. So the distance of this point from the origin is, you know the distance formula. So if you have a point here xy, so this length here will be, it is actually going with the square root, but when we square both sides, we can eliminate the square root sign. Or you can say Pythagorean, you can use right triangle here. This length will be x and this will be y, and this one is hypotenuse, so you can easily write this. So our goal is to find df dt. Now I plug my y value here. So the simplified version gives me now variable with only x. So now we are taking derivative with respect to t. So this gives me 2f df dt. This x square gives me 2x dx dt. 48 and then x gives me dx dt. And this is a free constant. Now we need to plug all these values here. First we need to see what is our f. So you can use the Pythagorean, this one here. X is 4, y is 20. So when I plug it here, we need to simplify for f. So f gives you square root of 4 square plus 20 squared. And then the simplified one is 4 square root of 26. You can plug it back here. And then calculate df dt, dividing both sides by 8 square root of 26. So this is our final answer. You can further simplify as 14 square root of 26 over 13. Okay, next. The volume of a spherical balloon is increasing at a rate of 6 cubic feet per second. How fast is the radius changing at the instant when the radius is 2 centimeters? So the volume of a spherical object or balloon will be 4/3 pi r cubed, where r is the radius. Okay, this is given to us. Also we are given dv dt, which is 6, that it says increasing at a rate of 6 cubic feet per second. So the goal is to find the rate of change of radius, which is dr dt. So we take the derivative from here with respect to t. We get dv dt on this side. I could use here uppercase V, so that I'm using here. And then the derivative on this side, 4/3 pi is a constant. R to the 3 gives me 3r squared dr dt. Now we need to plug all information we have and then simplify for dr dt, which is 3/8 pi. We are done for this problem. Next, air is pumped into a spherical balloon at a rate of 6 cubic feet per second. How fast is the radius increasing after 3 minutes? Now the information is a little different. It did not give us exact measurements, but it says after 3 minutes, assuming that initially the balloon has no volume. We can say 0 volume. Okay, so given volume of the sphere is this equation we know. The rate of change of volume is given. Goal to find dr dt when when t equals 3 minutes. So assume that the volume of the balloon is 0 at time t equals 0. So then we can say that 6 will be dv dt. And we have seen dv dt from here, which is 4/3 and then pi times 3 r squared. So then 3 cancelled out. That's why you get this. And you have seen this one in the previous example. So then dr dt is 6/4 pi r squared. Now the problem here is we don't know exactly what is r. So we need to figure out r. After 3 minutes, the volume will be 3 times 60 times 6. To convert this one to second, that's why I multiply by 60. And then rate will be 6. So this is your volume after 3 minutes. So then we just put this one here. V equals that number and then solve for r. So r to the 3 is this one. Then your r will be cube root of this. So that one will put here and square it. So you can see now 6/4, I can reduce it to 3/2, then pi is there. I have r equals this value and then square. So makes it 2/3. So this is my exact answer. If you want, you can use your calculator and write your answer as a decimal.